Have you ever been writing a Python script? Maybe it's just a simple hello world or, perhaps a really complex web application and you hit run, and just for a second you wonder, what actually happens under the hood? You might have heard Python is an interpreted language, but, well, if you're like me, that only scratches the surface. It feels like there's more going on.
That's a really common way to think about it.
Yep.
But yeah, the reality is far more intricate and honestly quite fascinating.
Yeah.
Today, we're not just scratching the surface. We're doing a deep dive into Python's sophisticated engine room, these core components that really bring your Python code to life. We're talking about Python bytecode and the Python virtual machine, the PVM. Our mission here is basically to give you a shortcut to being genuinely well-informed about this often mysterious part of Python, maybe with some surprising facts along the way.
Okay, let's unpack this then. If Python isn't just directly interpreted line by the CPU, then, well, what is happening? Why does it need these extra steps? Seems complicated.
Well, the fundamental challenge you see is bridging this huge gap. You've got the elegant, human-readable Python code we write on one side, and then the raw binary instructions a computer's processor actually understands on the other. Totally different worlds. Python tackles this with what's really a hybrid execution model. Think of it like this. Your Python code is a brilliant high-level script for a play.
Okay, like stage directions.
Sort of, but even higher level initially. But before the actors, that's your computer's CPU, can perform it, that script needs to go through two crucial transformations.
So it's not like the CPU just picks up our .py file and starts performing directly.
Exactly. No, first your script gets compiled, not to machine code directly, but into an intermediate low-level representation we call bytecode. Now, this bytecode, it's like a universal set of detailed stage directions and cues, really specific, but it's designed for any PVM, not a specific actor or a specific type of computer.
Universal stage directions. I like that. Platform independent.
That's the key word. It's wonderfully platform independent. Then what happens?
Right, so we've got these universal directions. Who's the director?
That's where the Python virtual machine PVM steps in. The PVM is absolutely the director for this play. It takes those universal bytecode instructions and interprets them, translating them into concrete actions for the actual hardware and operating system underneath.
Okay, so that two-step process, source to bytecode run by PVM, that's the secret sauce for portability.
That's exactly it. Because the bytecode is universal, you can write your Python code on, say, a Windows machine, and it'll run just the same on a Linux server or a Mac. As long as they have a compatible PVM, it really delivers on that write once, run anywhere promise.
And you mentioned efficiency, too. Something about .p files.
Yes, that's another neat part of this system. Once your code is compiled to bytecode, Python is clever enough to often save it. It puts these compiled files, usually with the .pyke extension, in a special PyCache directory. Now, if you run the script again and the source code hasn't changed, the PVM can just load and execute the .p file directly. Skips the whole compilation step.
So that's why sometimes the second time I run something, it feels faster to start up.
Precisely. It significantly speeds up startup times, especially for bigger projects with lots of modules.
That makes a lot of sense. Okay, so we've got source code to bytecode. PVM runs the bytecode. Let's really dig into the what now. How does our nice, clean Python code actually become that bytecode? And then how does the PVM execute it step by step?
Right, the journey starts with something called lexical analysis. Python's scanner basically dissects your script, breaking it down into the smallest meaningful pieces, keywords like def or if, variable names, operators like plus or. We call these tokens.
Like identifying all the words and punctuation in a sentence.
Exactly like that. Then comes parsing. The parser takes these tokens and arranges them into an abstract syntax tree, or AST. Think of the AST as a hierarchical logical structure that represents your code's meaning and how the pieces relate.
And if my syntax is wrong, like a typo.
That's where it stops you. If the parser can't build a valid AST because the syntax doesn't make sense, you get a syntax error right there. Game over before it even gets close to bytecode.
So the AST is really the blueprint. If the blueprint's flawed, you can't build the house.
Perfectly put. Assuming the AST is good, the compiler takes over. From that AST, it emits a sequence of bytecode instructions, or opcodes. Each opcode is a single, low-level operation the PVM understands. Things like load concatenate const to push a constant value onto a stack, or binary add to pop two things, add them, and push the result back.
Low level, but still not machine code, right? Still for the PVM.
Correct. Still for the PVM. And these opcodes often have arguments like which constant to load or which variable name to look up. All of this bytecode, plus other info like the constants table and variable names, gets bundled up into what's called a PyCode object.
Okay, Pycode object holds the bytecode. Now, I've heard Python even does some little optimizations right here. Like if I write x equals 10 plus 20.
That's a great observation. Yes, it does. That's an example of constant folding. It's a basic type of Peephole optimization. The compiler sees 10 plus 20, knows the result is always 30, and just puts 30 directly into the bytecode, saves the PVM a tiny bit of work later.
Clever. Shows they're thinking about performance early on.
Definitely.
So once we have this optimized Pycode object packed with bytecode, the PVM finally takes center stage. How does that work? Especially in CPython, the one most of us use.
Right. CPython's PVM is primarily stack-based. It uses an evaluation stack. Imagine a stack of plates. Most bytecode instructions either push data onto this stack, pop data off it, or manipulate the items right on top.
So the loadicon SD pushes a value onto the stack.
Yep. And binary ID would pop the top two values off the stack, add them.
And push the result back on top.
You got it. It's a very common and efficient way for interpreters to work.
Okay, the stack makes sense for operations. But what about function calls? I hear about frame objects. Where do they fit in?
Excellent question. Frames are crucial. Every time you call a function, Python creates a new frame object for that specific call. Think of it as a dedicated workspace for that function's execution.
What's in the workspace?
It holds everything that function needs. A reference to its code object, fcode, its local variables, flocals, the global variables it can see, fglobals, and even a link back to the frame of the function that called it fback. Critically, it also keeps track of the instruction pointer, flasty, which tells the PVM which bytecode instruction to execute next within that function.
And these frames stack up, right? The call stack.
Exactly. As functions call other functions, their frames get pushed onto a call stack. When a function finishes and returns, its frame is popped off. Standard computer science stuff, but Python implements it very neatly. And the absolute heart of the PVM is its main execution loop. In CPython, this happens largely inside a function called pyeval framex. This loop just runs constantly, following a simple fetch, decode, execute cycle. Fetch an opcode, figure out what it means, decode, do it, execute, over and over again.
Fetch, decode, execute. Got it. It sounds incredibly efficient, but also like there's a lot going on behind the scenes that we just, take for granted when we write Python.
Oh, absolutely. The PVM isn't just executing bytecode instructions one by one. It's also managing some fundamental Python behaviors.
Like what?
Well, first, memory management. This is huge. Python handles memory for you automatically, mainly using reference counting. Every single object in Python has a hidden counter, tracking how many references point to it. When that count hits 0, poof, the memory is immediately freed.
Seems simple enough.
It is, usually.
Ooh.
But there's a catch. Cyclic references. Imagine object A points to object B and object B points back to object A. Even if nothing else points to them, their reference counts will never reach 0.
Ah, so they'd leak memory.
They would, except CPython has a backup plan, a generational garbage collector. It runs periodically, specifically looking for these unreachable cycles and cleans them up. It's a clever two-part system.
Okay, memory management. What else?
Dynamic typing. Python checks types at runtime, not compile time. The PVM makes this happen. When you do a plus B, the binary ID opcode actually has to look at the types of A and B right then to decide. Is this number addition, string concatenation, list merging?
That's the flexibility we love, right? Duck typing.
Exactly. It's called dynamic dispatch. The same operation can behave differently based on the objects involved.
Makes sense.
Then there's name resolution, how Python finds variables. It uses the LEGB rule, local, enclosing function locals, global, built in. The PVM uses specific opcodes like loadfast for locals, because they're fast to access in the frame, or low-age global to search module-level names.
LEGB. Right. And finally, the big one, the GIL.
Ah, yes, the Global Interpreter Lock, or GIL. It's a mutex, a lock that's really fundamental to CPython's design. Its main job is to protect access to Python objects, making memory management simpler and making it easier to write C extensions. It does this by ensuring only one native thread executes Python bytecode at any single point in time within a CPython process.
Only one thread, even if I have multiple CPU cores.
Correct. For pure Python code that's CPU-bound, just doing calculations, only one core will be executing Python bytecode at a time because of the GIL.
So that's why standard Python threading isn't great for speeding up heavy math stuff.
Precisely. For CPU-bound tasks, the GIL effectively serializes execution. However, and this is important, for I/O-bound tasks, things like waiting for network data, reading a file, waiting for a database query.
Things where the program is just waiting.
Yes. During those waits, CPython often releases the GIL. This allows another thread to grab the GIL and run its Python code. So for applications doing lots of I/O, threading can still provide concurrency and responsiveness, even with the GIL.
Okay, so the GIL isn't always a bottleneck. It depends on the workload.
Exactly. And if you need true parallelism for CPU-heavy work in CPython, you typically reach for the multiprocessing module, which sidesteps the GIL by using separate processes, each with its own interpreter and its own GIL.
That distinction between IO-bound and CPU-bound is critical for understanding the GIL's impact. Now, you mentioned bytecode earlier. How can we, as developers, actually see this stuff? Peek behind the curtain.
Python gives us a fantastic tool for that. It's the built-in dis module. Dis stands for disassemble. You can import dis and use its dis function on your Python functions or code snippets. It prints out a human-readable version of the bytecode.
So I could define a simple function like def add a,
Yeah.
return a plus b, and then just dis.disadd.
Yep. And you'd see the opcodes. Probably load fast to load A, load fast to load B, then binary add, and finally return value.
That sounds incredibly useful for understanding what's really going on, maybe even for debugging tricky performance issues.
Absolutely. I remember using it once on a function that was unexpectedly slow. Running dis showed me it was creating temporary objects inside a tight loop, something totally not obvious from the source code. It pointed right at the problem. It's like getting hints directly from the interpreter.
Wow. Okay, I'm definitely going to try that out. So, we've dug deep into CPython's engine room. But is CPython the only game in town? Are there other ways Python runs?
Not at all. And this is a really important point. The Python language is defined by a specification. CPython is just one implementation of that specification, albeit the main reference one. There are several other major implementations, each with its own unique engine room and different strengths and weaknesses.
Different engine rooms, so they might handle bytecode or the PVM differently.
Exactly. Let's look at a few key ones. First, there's PyPy. PyPy's main goal is speed. It uses a technique called Just-In-Time JIT compilation.
JIT? How's that different from CPython's approach?
Well, CPython mostly interprets bytecode instruction by instruction. PyPy starts off interpreting too, but it watches your code as it runs.
Oh.
It identifies bits of code that are executed frequently, so-called hot code paths, and compiles those specific parts down to highly optimized native machine code right there at runtime.
So it gets faster the longer it runs.
Often, yes. For long-running, CPU-intensive code, PyPy can be significantly faster than CPython. And another big thing, PyPy effectively does not have the CPython GIL, which could be a huge win for multi-threaded CPU-bound tasks.
Interesting. What are the downsides? Compatibility.
That can be the main one. While PyPy's compatibility with C extensions has improved massively, it's not always 100% seamless like CPython. You need to check if your dependencies work.
Okay, so PyPy for speed, potentially. What else?
Then you have Jython. Jython runs on the Java Virtual Machine, JVM. It compiles your Python code not to Python bytecode, but to Java bytecode, the .class files that JVM understands.
Whoa! So you can run Python on the JVM. Why would you do that?
The huge advantage is seamless integration with the Java ecosystem. You can import and use Java libraries directly from your Jython code and vice versa. It's perfect if you're working in a heavily Java-based environment. And like PyPy, no GIL.
Makes sense for Java shops. Is there a .NET equivalent?
There is. That's IronPython. It's designed for the .NET Common Language Runtime, CLR. Similar to Jython, IronPython compiles Python code into Microsoft Intermediate Language, MSIL, which is the bytecode for the .NET platform. Again, the big win is tight integration using .NET libraries from Python, embedding Python scripting into .NET apps, and also no GIL.
So CPython, PyPy, Jython, IronPython. Quite a few choices for the engine room. This obviously leads to the big question, how do you choose? Which one is right for a given project?
Yeah, it really boils down to your specific requirements and constraints. CPython is the default, the standard. It has the widest library compatibility, especially with C extensions, the largest community, and it's the most mature. For general-purpose Python development, it's almost always the starting point.
Okay, start with CPython unless you have a specific reason not to.
Pretty much. You choose PyPy if raw performance for CPU-bound Python code is your absolute top priority, and you're okay with potentially managing some C extension compatibility issues. Think scientific computing, long-running servers.
Right. And Jython, IronPython.
You'd opt for Jython specifically for deep integration with existing Java applications or libraries. If your world is Java, Jython is your bridge. Similarly, IronPython is the choice when you need to live within the .NET ecosystem, leverage .NET libraries, or embed Python in C# or VB.NET applications.
So it sounds like a key factor, apart from ecosystem integration, might be that GIL again. If you have a multi-threaded CPU-bound workload, PyPy, Jython, or IronPython might offer parallelism that CPython just can't provide with standard threading.
That's often a major deciding factor, yes. If true multi-threaded CPU parallelism within a single process is a deal breaker and you can handle the library situation, then one of the non-CPython implementations becomes very attractive.
What an incredible journey, really, through Python's internal machinery. It's amazing that the language feels so simple and readable on the surface. But underneath, there's this really sophisticated foundation of bytecode, the PVM, memory management, the GIL. It's a testament to thoughtful design, making the complex feel simple.
Absolutely. And exploring this engine room, you realize that understanding these internals isn't just, academic trivia. It genuinely empowers you as a developer. Knowing how this works helps you write more efficient code. It helps you debug those really weird, complex issues with much greater insight. And it helps you make smarter architectural choices, especially around performance and concurrency.
It really turns Python from maybe a bit of a magic black box into something more transparent and understandable.
Exactly.
So what does this all mean for you, the listener, the curious programmer, maybe teaching yourself this stuff?
Well, we hope this deep dive encourages you to maybe peek behind the curtain of your own code a bit more often. Think about it. How might digging into the bytecode of one of your projects, maybe using that dis module we talked about, how might that change the way you think about optimizing it? Or even just deepen your appreciation for how elegant Python really is under the hood?
A fantastic question to ponder. Thanks for diving deep with us today into Python's engine room. Until next time.